There's this really strange, powerful force of physics working all around us, and most of the time we don't even see it. It's kind of like a ghost in the machine, a swirling current that can slow things down, heat things up, and even melt solid metal. So today, let's pull back the curtain and see what's really going on. All right, let me start by asking you a question. Imagine you've got two identical pipes. One's made of copper, a conductor, and the other is plastic, an insulator. Now, if you drop a strong magnet through that plastic pipe, it falls exactly like you'd expect. But if you drop it through the copper pipe, something really weird happens. Why on earth does it fall so slowly?
And hey, this isn't just some hypothetical question. Our source material describes this exact same setup, dropping a magnet through an aluminum pipe, another conductor, versus a PVC pipe. And the result is, well, it's pretty wild. The magnet takes way longer to fall through the aluminum. There's no trick here, I promise. It's pure physics.
I mean, the difference is just staggering. In the PVC pipe, the magnet is basically in free fall. But in the aluminum pipe, it's almost like it's falling through invisible honey. So there's got to be some invisible force pushing back against gravity. But what is it?
Well, the culprit is a phenomenon that was actually discovered way back in the 19th century. It's an electrical current, sure, but it's not the kind that flows neatly through a wire. No, this one swirls and churns right inside the metal itself.
And they have a name, eddy currents. The physicist Foucault, the guy who discovered them, named them after the swirling eddies you see in water. Which, when you think about it, is the perfect name. Anytime a chunk of metal moves through a changing magnetic field, or a magnet moves past the metal, these little whirlpools of electric current pop into existence inside the conductor.
Okay, so here's the classic way to picture this. Imagine a copper plate swinging like a pendulum right through a strong magnetic field. As the plate swings in, the magnetic flux, which is really just a fancy way of saying the amount of magnetic field passing through it, goes up, creating eddy currents in one direction. And as it swings out the other side, the flux goes down, creating currents that swirl in the opposite direction. Now here is the absolute key. According to the laws of physics, these swirling currents generate their very own magnetic field. And that new field always opposes the change that created it in the first place. To put it simply, it pushes back. It's like hitting the brakes. This creates a powerful braking force. It's called electromagnetic damping that slows that pendulum or our falling magnet right down. Okay, so this braking effect is super cool, right? But for a long time, engineers actually saw these eddy currents as a huge pain. They were this fundamental problem in electromagnetism that they were just constantly fighting against. And here's why. Think about something like a transformer or an electric motor. They've got metal cores with coils of wire wrapped around them, all with changing magnetic fields. It's a perfect recipe for eddy currents. And these currents do nothing useful. They just heat up the metal core. That heat is just wasted electricity. It makes the whole device less efficient. It really is like a tiny ghost in the machine, just stealing your power. So this was a massive headache for early electrical engineers. They needed the metal cores for their devices to work, but they didn't want these energy-sucking eddy currents. So the big question was, how in the world do you tame a ghost current you can't even see?
Well, the solution they came up with is, honestly, it's just brilliant in its simplicity. It's all about one thing, breaking up the swirl. See, instead of using one solid block of metal, they decided to slice the core into a bunch of really thin sheets. They call them laminations. Then they coat each one with an insulator, like lacquer, and stack them all together. This clever design makes it impossible for those big, swirling eddy currents to form. They get trapped inside each tiny sheet, becoming these weak little currents that generate hardly any heat. And boom, problem solved. But hold on, the story doesn't end there. Not even close. Because what started out as this annoying problem eventually became an incredibly useful tool. Engineers realized that if they could control this invisible braking force, they could turn this ghost into a superpower. And the uses they came up with? They're all over the place, and they're seriously clever. We've managed to harness them for everything from bringing high-speed trains to a screeching halt to stabilizing super-sensitive lab equipment and even powering those old-school electric meters that used to be in everyone's homes.
Okay, let's take magnetic braking on trains, for example. You've got these powerful electromagnets that get lowered down toward the steel rails. This creates massive eddy currents inside the rails themselves, which in turn creates a magnetic field that fights the train's motion, slowing it down. And the best part? It's an incredibly smooth system with no mechanical parts to wear out. No friction, no brake pads, just a silent, invisible force. Or what about this? Induction furnaces. By blasting a high-frequency alternating current through a coil, you can generate these absolutely enormous eddy currents inside a piece of metal sitting inside it. These currents produce so much heat that they can literally melt the metal, all without a single flame ever touching it. It's an amazingly clean and precise way to create things like metal alloys.
You see, it all comes back to that core idea from our source material. This retarding force, this braking force, is the whole key. Whether it's gently slowing down a tiny magnet in a tube or bringing a 200-ton train to a dead stop, the physics is exactly the same. We've just gotten really, really good at controlling it.
So, what started as a simple physics puzzle, a magnet falling slowly through a pipe, has turned into this powerful engineering tool that literally shapes our modern world. It really makes you wonder, doesn't it? What other invisible forces, these ghosts in the machine, are out there working all around us, just waiting for us to understand and harness